is Dan Combest, one of the CFD engineers here at ENGYS, and today I'm going to talk about porous media modeling with HELYX. As always, I like to start with some webinar goals, and I'd like to introduce some important considerations with porous media and CFD simulations, and hopefully by the end you'll obtain a sense of how porous media can be set up within HELYX. I hope to accomplish this in around 20 minutes, maybe a little bit longer. We'll answer all the questions via email post-webinar. So first off, we'll start with the role of porous media models, then we'll talk about some important simulation considerations, then I'll dive into a learn by example, and leave you with a few take-home messages. So first off, the role of porous media. Well, we can start all the way with Navier-Stokes. The Navier-Stokes equation is really just a force balance on the system. This means that we have components that deal with acceleration, maybe on the left side of the equation, and then we have other terms that deal with forces. Forces that are below the continuum scale, we use a constitutive model. And the most classic one that deals with the Navier-Stokes equation is Newton's law of viscosity. So we approximate all the molecular interactions, the things that we don't want to resolve within the mesh, viscous forces. We resolve this with Newton's law of viscosity. Forces can also be handled with boundary conditions, but other forces that aren't directly modeled, we can use source terms. And some of the more classic examples would be GRF for capturing tire tread rotation influences, if you saw my other webinar, moving reference frame for turbomachinery to approximate Coriolis forces, and then also capturing the influence of small geometric details not explicitly captured by the mesh, and that's really what the focus is today. So first off, we can talk about volume sources. And the first one that comes to mind is an exponential model. In this type of model, porous media is assumed to be isotropic, and it takes the form of this kind of model where we can fit C0 and C1, which are dimensionless constants. We can fit our data to this model. A more commonly used porous media model is called the Darcy-Forchheimer model, in which pressure drop is due to viscous and inertial losses through complex geometry. So not only is it a little bit more phenomenologically agreeable, so it agrees more with the physics, it also allows us to model isotropic and anisotropic porosity. And the form of this model is really two main terms. There's a viscous loss term right here, in which we have a viscous loss coefficient tensor. And in this tensor, we're able to do directionally specific viscous loss coefficients. And then in the other term, we have an inertial loss coefficient tensor. As I mentioned before, forces can also apply to the system through boundary conditions. There's two main boundary conditions within HELYX that deal with this, besides fixed pressure, pressure gradient, any other pressure boundary condition, but something with pressure drop. The first one is a porous baffle. So this is used where maybe a cell zone can't necessarily be resolved, so maybe it's too thin, and the pressure loss in the device is very small. The form of this is very similar to a Darcy-Forchheimer model, in which we do have a D and F, but we also need to provide the thickness of the baffle in order to capture this model more effectively. The next one would be resistive outlet. It's a situation where a fixed pressure outlet is related to downstream geometry or other resistances. So it's a combination of resistive pressure and resistive velocity boundary conditions. And you can see again it has kind of a similar formulation to a Darcy-Forchheimer, but we also have a static pressure, and we also have some other components that are related to the tangential loss coefficient. So this is for fixed value pressure using resistive pressure, and then we also have a velocity component for a resistive velocity boundary condition. Some important simulation considerations when talking about porous media. First off, meshing. There's two main activities that one might be doing if you're setting up porous media or baffles or something like that within your system. The first is creating cell zones for sources. Within each surface, there's a tab called zones, and within zones, we're able to set the type, and then we also need to make sure that we check this cell zone box and give it a cell zone name. Modeling porous media with a volume source must have a cell zone. Type internal is the most common approach. It's not the only approach, but for today, I'm just going to consider type internal. Now for baffles, on the other hand, we could use type boundary. We would really need to just provide a face zone name, and because it's just a boundary condition, and we're just only creating this baffle boundary condition, we don't need to create a cell zone. We also need to make sure that we're using freestanding face zones. One of the important steps in the whole process is making sure that you've prepared the data and you have accurate coefficients that you're introducing into your porous media model. First, you would need to obtain a pressure drop versus velocity data plot. You also need to make sure that you have porous media thickness in the direction of the flow, the density of the fluid that's going through, the fluid viscosity, kind of basic understanding or basic knowledge of what the fluid is that's moving through this porous media. Next, you need to plot a delta P over L on the y-axis versus velocity and fit a polynomial with a zero intercept. So this is a second order polynomial. Next, we take these coefficients that are output from our curve fit, and then we need to determine D and F. So within the setup tab, one point I'd like to make, so not only do we need to know the directional specific viscous loss and inertial loss coefficients, but we also need to define, if we're using a Cartesian coordinate system, we need to define E1, E2, and E3, which are all orthogonal vectors. It's a local coordinate system, so it represents a local coordinate system in the x prime, y prime, z prime. All of our viscous loss and inertial loss coefficients are with respect to these different local axis vectors. And you'll notice that we've only got E1 and E2 because once we have these two vectors, then we know that E3 is orthogonal to that. If we're looking at cylindrical coordinates, we still need to define the viscous loss and inertial loss coefficients in E1, E2, E3 coordinate system, but E1, E2, and E3 represent a local cylindrical system. So R prime, theta prime, Z prime, and really we only need to provide the Z prime because we can infer the rest. For porous baffles, so we talked about setting up porous media, but if we're talking about a porous baffle, we're looking at something called a cyclic AMI, and if we're looking at a resistive outlet, it's a little simpler in that it's just a straightforward outlet boundary condition. For a porous baffle, really we need to set up our cyclic AMI, but then we need to set the type to porous baffle and set our viscous loss coefficient, our inertial loss coefficient, and then our porous length to accurately set up this porous baffle boundary condition. For the resistive outlet, it's a little simpler in that we use a standard pressure outlet, but instead of using a fixed pressure, maybe 0 if we're doing an incompressible flow, we'll set this to resistive, then we'll set the downstream pressure, the linear loss coefficient, the quadratic loss coefficient, the tangential loss coefficient, and that's everything we need to know about the resistive outlet. Everything else is set automatically. All right, time for the learn by example component. Today, I'd like to set up a case in a water filter geometry. In this case, there's an inlet here at the bottom. There's also a cylindrical porous media, and the flow comes in the geometry, it flows through the porous media, and then it flows through the outlet. The boundary conditions today, I'd like to use a static pressure inlet, also use a fixed mean pressure at the outlet. The porous media coefficients today are 9.5 e to the 5 and 400 for D and F, respectively. I'd like to evaluate the flow through the device, distribution within the porous media. I'd like to look at the overall flow rate, and then also just in general look at the flow path. All right, so I will start with just an empty HELYX case. And when we start HELYX, we're met with a mesh setup solver and view tab. So to start the meshing process, I need to specify the background mesh spacing. And so here we're going to do 0.0025 meters. Now let's import the geometry. All of these were in a triangulated surface. And so here we've got, you'll see our inlets and outlets, and then there's some shells and caps. We've got our actual filter, which is going to be our cell zone. We've got our inlet. our inlet port, our our inner shell, our outer shell, and then our outlet. So we've set the background mesh. Let me go ahead and make this a little easier on myself and just select all of these and set the local refinement to 1:1. Really, the main point of this is setting up the filter. So first off, I'm going to set the inside refinement to 1 because I'd like just a little bit more refinement inside of this filter itself. Next, let's go to the Zones tab. Let me set it to type internal. Let's create a cell zone, and that's all I need to do. Just for good measure for today, because I've meshed this case before, let me go to Mesh Options. And then in terms of snapping, let me set the global region snap, just so I get a little bit cleaner approximation, cleaner snapping of the geometry. Next, I need to set the material point. Let's do -0.025. And then if I wanted to, I could actually create the mesh and then go through and set up the boundary conditions. But for now, let me just hit virtualize. And what virtualize does is it assumes all of my boundary conditions, all of my surfaces become boundary conditions, and all of my zones become cell zones. So you can see that I've got my cell zone here, and I've got all my boundary conditions. It allows me to go further in the process to set up this simulation. So first off, let's do segregated, steady, incompressible. It's all single phase. Let's change the material to water. For modeling, I'm going to leave default K omega SST for RANds. And then really for inlet, I just need to change it to type inlet. Let's do a fixed static pressure of 2. And then for outlet, set it to type outlet. Let's do a mean pressure of 0. Now for the cell zone, here's where we need to actually set up the porous media. So let's do porous medium, Darcy-Forchheimer. Let's do 9.5 e to the 5. And then let's just make sure that flow doesn't happen in the other directions. Let's just do 1 e to the 7 and 1 e to the 7. And then for inertial loss, let's do 400. Let's do 10,000. Now what I've done here is, because we're going to use cylindrical coordinates, it's only going to allow flow in the R direction, so inward from this outer shell to the inner shell down to the outlet. And let's see, for the origin, I'll leave the origin, and then for the z-axis, coincidentally, it aligns with the Cartesian z-axis, so I can leave everything the same. Numerical schemes, I'll leave the defaults. Solver settings, I'll leave this. Runtime controls, let's run it for 2000 iterations. Field manipulation, I'm not going to add anything. For monitoring functions, let's add a volume report. And this volume report will give us the min, the max, and the mean of K omega pressure and velocity. Let's do that. Let's also do a volume report on the filter itself, just so we have a little bit more information about specifically what's happening inside of the filter. And so to do that, I just need to select the filter cell zone. Let's also do some surface reports, just so that we can be confident in our assessment of overall pressure drop. So let's do an area weighted average of pressure at the inlet. We know that's going to be 2, but let's just do that to prove to ourselves that it is. Let's do a surface report at the outlet. Area weighted average of pressure at the outlet. And then finally, I really want to try to understand flow uniformity at the boundary of this filter. So let's do a surface report on the filter. And let's do flux weighted averaging, but really let's look at everything but pressure. And then in terms of phase zones, this is going to be on the filter itself. Next, for flow initialization, let's do potential flow, let's do Prandtl mixing length initialization for K and omega. All right, at this point, I would hit run all, and run all would mesh, setup, and solve, and then we would wait for our result. Luckily, I've already run this case. We've done the setup. Now let's look at what kind of results we would get. So first off, we're on the View tab. We're looking at streamlines going through the porous media towards the outlet. All right, so this is kind of just more of a sanity check to show us that yes, the porous media is only allowing the flow to go in the radial direction. We do see a little bit of swirling, but this is behind the porous media itself. Okay, so some of the questions that we wanted to ask ourselves are, what's the flow rate coming through the device? So we've got our outlet. So let's look at the flux. We can look at the flow rate. This is about, let's look at 1.2 e to the minus 4 meter cube per second. We're talking about gallons per minute. Maybe around 1 gallon per minute. Let's look at the pressure drop. So right now the fixed mean pressure is at around 0, which is what we set. We see a band of min and max pressure. We can see the pressure curve is very flat. Let's look at the inlet. Again, we expect the flow rate to be around the same. We expect homogeneity to be around 1. We expect pressure to be at the fixed value that we actually fixed in our simulation. Great. Let's look at the volume report. So the volume report is a great tool for us to look at the min, the max, and the mean value of pressure, velocity, and then the turbulence parameters. So we can see for velocity, it peaked initially as we're starting to converge, and then we see it flat. We see a flat band. We see the same for K, turbulent viscosity, omega, and pressure. So we can use this to really assess the convergence behavior of the simulation. Let's look at the zones. This is a volume report specific to the zone, so we can see that the velocity, the K, the turbulent viscosity, the omega, and the pressure all are flat through the zone, so we can say yes, this case also has good convergence behavior. We could also look at the filter surface report, so we can assess kind of the uniformity through the system. We can use homogeneity. So if we saw homogeneity equals 1, then that means that everything is perfectly spread over the boundaries of this zone. And we can really take a look at velocity, K, omega, and then pressure. And we can see that there's some inhomogeneity in the flow through the porous media. And we can also kind of see this through the streamlines themselves, to where we have this huge velocity pushing in, and then we see some recirculation around this ring, around the filter, and then we see a lot of flow pushing in at the top of this filter versus flow pushing in more towards the bottom. So we see kind of this inlet jet. So this might help us in our design. Maybe we need to put baffles or some sort of devices to help redirect some of the flow earlier on. Maybe we can look at a different material for the filter itself, or maybe we can just really redesign the outer shell of this filter. So we wanted to answer a few questions. We wanted to look at homogeneity. We wanted to kind of get a good perspective of how flow is moving through the device, and then also look at the flow rate. And this is exactly what we've done within HELYX. Okay, so let me jump back to the slides. I've talked about porous media inside of HELYX. We have another product called Elements, which is more related to automotive. And within Elements, there's actually a very interesting tool that speeds up the process of setting up porous media. So sometimes we still want to use a Cartesian coordinate system, but our radiators may be tilted because ride heights have changed in vehicles. So we have a nice tool within Elements that allows us to select the flow direction, the transverse direction, to help us kind of orient the different axes that are within our system so that we can set everything more correctly in our automotive simulation. So it's a little bit easier within Elements. Let me leave you with a few take-home messages. First off, porous media allows us to model and approximate complex physics without actually resolving the small structures with mesh. This is huge for CFD because our mesh counts can drop dramatically. There are several porous media models, and pressure loss models that are available within HELYX. These can be source terms, these can be baffle boundary conditions, these can be resistive outlet boundary conditions. They're all very useful, and as an engineer, we need to be creative in how we apply these and correlate them with our expectations and correlate them with our experimental data to accurately resolve the behavior of different devices. And HELYX really enables users to easily set up these porous media models all the way from meshing down through post-processing. So thank you very much for coming today. And if you have any questions, please hit reply on the email and I will get back to you. Thank you.